Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May June 2023, Paper 4, Variant 2. In today's lesson, we will talk about electromagnetic induction and alternating current. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these two topics, and also you can have better understanding of these questions. Let's study together, let's improve together. Question 6 says, a heavy aluminum disc has a radius of 0.36 meters. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field of flux density 0.17 Tesla is switched on. This magnetic field is perpendicular to the plane of rotation of the disc as shown in figure 6.1. So if you look at figure 6.1, we have magnetic field. So this is magnetic field. So these arrows are representing the magnetic field. So we can draw some arrows here so you can get better idea about this one. So these are the arrows representing magnetic field. So the area we have to consider, that area has to be perpendicular to these lines, means area perpendicular. So angle has to be 90 degrees. This area we have to consider. So simply we can draw these lines here. So this area we have to consider. So this area is perpendicular to magnetic field lines. You can also understand like this. Imagine that this my hand, this one is the disc, and magnetic field is passing through this area. So we have to consider this area because this is perpendicular to magnetic field lines. So simply for this question we can write down flux, magnetic flux. This is the product of magnetic flux density times area perpendicular to magnetic field. And we have to define this one, so simply you can write down these points. You can say product of magnetic flux density, this as M mark, so it has to be in your answer. And second part you have to write down area perpendicular to the magnetic field. So you will get 2 marks if you have written this. Second part says calculate the magnetic flux through the disc. Give a unit with your answer. Now simply we have to use the formula. We have already discussed that magnetic flux is equal to magnetic flux density, the product of magnetic flux density and area perpendicular to magnetic field lines. If you look at given informations, we have the value of magnetic flux density. So simply we can enter this is 0.17 Tesla. And area perpendicular means the area of the disc. Area of the disc, this is a circle, so this has to be pi r square, and value of radius we have. So this is 0.17. Here we have pi, and the value of the radius of the disc is given, that is 0.36 square. If we solve this one, we will get 6.9 times 10 to minus 2 Weber. So this is WB. So simply we will write down here 6.9 up to 2 SF because the least number of SF in raw data we have 2 SF. And so we are using 2 SF here. So this is the right physics. You can also use 3 SF, but 2 SF is the right physics. So we can write down this is 10 to minus 2, and the unit of this one is WB, Weber. This question has 2 marks. The first mark you will get if you have written this expression, you will get 1 C mark. Then the second mark is the answer mark if you have got the right value of magnetic flux and you have written the right unit, you will get 2 marks. Part B says the disc is rotating at a rate of 25 revolutions per second. Calculate the magnitude of the electromotive force induced between the axle and the rim of the disc. In this case, induced EMF is equal to rate of cutting magnetic flux. Rate of cutting magnetic flux. So we can write down here EMF in this case is rate of cutting magnetic flux. It simply means that the flux passing through the disc over time taken, and this time taken has to be time for 1 complete cycle, means when disc rotate 1 time. But for this question we have the frequency is given to us. Frequency is equal to 25. So we have frequency, this is 25 revolutions per second, it means this is 25 hertz. So we can find out time period, means time taken to complete 1 cycle. This disc is completing 25 cycles in 1 second. Now we need to find out time for one cycle. Time for one cycle will be equal to 1 over frequency, so this is 1 over 25. Now simply we need to plug in values. Flux passing through the disk, already we have, that was 6.9 times 10 to minus 2, we have calculated in the previous part. And the time we have, this is 1 over 25. So if we simplify, we will get 6.9 times 10 to minus 2 multiplied by 25. So if we solve this one, we will get 1.7 volts. So this is the EMF induced between the axle and rim of the disc. This question has 3 marks. First mark you will get if you have written that time period is equal to 1 over 25. So you will get 1 C mark. And the second C mark you will get if you have written this formula, you will get another C mark. And the last mark is the answer mark. If you have got the right answer, you will get 3 marks. Let's try to understand a little bit more about this part of the question. Imagine that magnetic flux density has been increased now. So magnetic flux density, you can imagine, is like this now. So magnetic flux density has been increased. It's a conceptual question, so try to answer this now by yourself. So imagine that magnetic flux density has been increased. If magnetic flux density has been increased but the frequency of rotation of the disk is not changed, so how about EMF? EMF will increase, or induced EMF will decrease, or it will remain constant. So try to answer this one first of all by yourself. So in this case, I hope you will say induced EMF will increase. So induced EMF will increase because induced EMF is equal to delta phi, means the rate of cutting of magnetic flux. In this case, this is equal to BA. So this is BA over delta T. So as B has increased, so this one has to increase. We can also understand this question in a different way. Now imagine that magnetic flux density is the same. So it is same as before, but disk is rotating slowly now. So rotate slowly. So the second case you can also consider, rotate slowly. So if disk is rotating slowly, how about induced EMF? It has increased or it has decreased? So first of all, try to answer by yourself. Okay, now let me explain to you. I hope you will say in this case induced EMF will decrease because delta phi means the magnetic flux, this is constant. If disk is rotating slowly, it means that delta T will increase. If delta T increase, it means EMF will decrease. So when you do some question, try to understand from other aspects as well. So this will help you to improve your understanding of physics. Part C says the axle and the rim are connected into an external circuit that enables the energy of the rotation of the disk to be stored for future use. Direction of rotation is shown in figure 6.1. Use Lenz's law of electromagnetic induction to determine whether the current in the disk is from the rim to the axle or from the axle to the rim. Explain your reasoning. This question is simply asking us to find direction of I induced. So we can write down direction of I induced. This is what we need to find out. I induced. Let's try to understand this one with the help of one simple example. Imagine that we have magnetic field. So these arrows, they are representing, these crosses, they are representing magnetic field. So in this case, our magnetic field is into the page. Now we can also imagine we have a rod. Imagine that the rod is placed inside this magnetic field. And now when the rod is at rest, there will be no induced EMF, there will be no induced current. Now imagine that we apply force on this rod, we hold this one and we move this one to the right. When we will move this one to the right, it will cut magnetic field lines. So as EMF is equal to rate of cutting magnetic flux, there will be induced EMF in this rod. And also we can find out direction of induced current by using right hand rule. So first of all, we can use right hand rule and we can find out direction of induced current. Right hand rule. So this one is the right hand, because this is generator effect. So you have to use right hand rule for generator, and for motor effect we use left hand. So that difference also you need to understand. In this case, current is induced, means current is produced, so it is generator, so you have to use right hand. So we have magnetic field. First of all, the index finger magnetic field is into the page and the force is to the right. So force is to the right, so it means current will flow in upward direction. So this is direction of I induced. So current will flow in this direction. And so this is the applied force. So this one is applied force. Now by Lenz's law, so let me use different color. Now by Lenz's law, there will be an opposing force on this one. So the opposing force, you can simply say it has to be in the opposite direction of applied force. Otherwise, we can also find out direction of opposing force. Now we have to use left hand rule because we have wire, it has current and the wire is inside the magnetic field, so we have to use left hand rule. So let me write down here. So we have to use left hand rule. So now take your left hand. In this case, magnetic field is into the page and current is in upward direction. So you will see direction of magnetic force, the direction of opposing force. This one will be to the left. So this is direction of F opposing. So we can say FOPB, opposing. So opposing force is in opposite direction of applied force. Let's try to discuss a little bit more before we answer this question. If you look at this explanation, what we have discussed here, it simply tells us that direction of induced current we can find by using right hand rule. We can also find direction of induced current by using left hand rule based on Lenz's law. Left hand rule, if you use here, this is based on Lenz's law. So this is based on Lenz's law. We can use left hand rule and we can find out direction of induced current. This question is asking us to use Lenz's law of electromagnetic induction. So it means that we have to consider opposing force and we need to find direction of induced current. So we will be considering Lenz's law to answer this question. If you look at this disc is the rim and here we have axle. So this one is the axle. We need to find out direction of induced current. Is it from rim to the axle or is it from axle to the rim? We will be looking at this point. So if you look at direction of rotation of this disc from this side, I mean if we look at this one from this side, what we will see this disc is rotating clockwise. So it means the applied force on this one is into the page. So we can write down here applied force is into the page. So I will say FA. So how about opposing force? Opposing force has to be out of the page. So I will say FOP. Opposing force out of the page. Now we have direction of opposing force. So I'll be writing here. We will use left hand rule, framing left hand rule. We have direction of opposing force that is out of the page. So this is direction of opposing force. This is out of the page and magnetic field in this case is to the right. So you have to use your left hand. So opposing force is out of the page. So it means it is pointing towards me out of the screen. So this is, and magnetic field is to the right. So current is in downward direction. So let me use different colors. So it means current is down here. So this is direction of current. So let me also draw this arrow here. So this is direction of current. So it means current is from rim to the axle. So it means this is rim to axle. You can choose any point. You will find direction of current is always from rim to axle. So this is how we can answer this question. I hope this is clear to you. Now let me show you the answer, how you can answer this. In your answer, you have to write down these points. So you have to include this one in your final answer. The first point, you can see current in disk is perpendicular to the magnetic field, and current causes force to act on the disk. Because there is induced current, that will cause opposing force. By Lenz's law, there will be opposing force on the disk. Means we are talking about this force. In this case, we can say this is over opposing force. Force opposes rotation of disk, so it has to be in opposite direction of rotation. So this is the second point. Third point, we have used the left hand here, and we can find direction of current, and current is from rim to axle. A beautiful question about Lenz's law. I hope this one is clear to you. If you still have any questions, please leave your questions in comments. Question 7 says 4 diodes are used in a bridge rectifier circuit to produce rectification of a sinusoidal AC input voltage Vin. Figure 7.1 shows part of the circuit, but 3 of the diodes are missing. The PD across the load resistor capital R is the output PD Vout of the bridge rectifier. State the name of the type of rectification produced by the bridge rectifier. Bridge rectifier is used to produce full wave rectification. So simply we can write on here full wave rectification, because with the help of bridge rectifier we can produce full wave rectification. Bridge rectifier, it consists of 4 diodes. For the second part, we need to complete figure 7.1 by drawing the 3 missing diodes correctly connected. Before we answer this question, so let me explain you one simple point. Maybe they can ask you next time. So full wave rectification. How we can achieve full wave rectification? One way to achieve full wave rectification is bridge rectifier. So we can use 4 diodes. So we can use bridge rectifier. Means we can use 4 diodes. So this is one way. And the second way is we can also do this one with the help of 2 diodes. We can also achieve full wave rectification. And half wave rectification, we can only use single diode. So this is full wave rectification. Now imagine that if this terminal is positive, so current will flow this way, then current will cross this junction and current will flow here. So direction of current will be this way through this resistor. So it means this side has to be positive, means current has to enter from this side all the time, and this side of resistor we can say it is negative. So if this is positive, so current cannot go this way because this is connected in reverse direction. So here we will have one diode, so we can draw the diode. So this has to be in the forward direction, forward. So this is how you can draw. Now when the current is at this point, current cannot go this way because this is at high PD. So this PD is greater, and current cannot flow from low to high. Current flow from high to low. So low PD. Current cannot go this way. So current has to go this way. So at this point, it has to be in forward direction. So simply we can draw over diode here. So current has to flow this way because this terminal is negative. Now let's try to understand when lower terminal, because this is AC, so when the lower terminal is positive, I mean this is positive, this one is negative, so current has to enter from this side, because full wave rectification means that current flow only in one direction. So if this is positive, current cannot go this way because this is connected in reverse direction. So current has to pass through this one. So this has to be in forward direction. So we can draw diode here. So it has to be in forward direction. So current will flow this way, and then current enter from here and it will pass through this. So it means this direction is right. And when the current is at this point, current cannot go this way because this is at high PD. It is connected with positive terminal, and this is at low PD. Current cannot flow from low to high, so current has to go this way. So current will cross this one. Now you see this one, for this current, this side is low now, and this one is high. So current can flow from high PD to low PD. So current will flow this way and finally enter here. So this is how you need to draw these diodes. I hope this one is clear to you. For the third part on figure 7.1, we need to draw an arrow to indicate direction of the current in resistor capital R. So arrow we have already drawn. So this arrow simply you need to draw. Let me explain you one important point. I have written here low PD and high PD, but it is better to say high potential and low potential, because PD is the potential difference across any component. Here we are talking about point. We are talking about this point. So this point is at low potential, so simply we can say low V, and this point is at high potential, we can say this is high V. And vice versa is also true. Means for this current, this point is at high potential and this point is at low potential for this current. So it's better to say low potential and higher potential instead of low PD and high PD. I hope this term is clear to you. For part B1 on figure 7.3, we need to sketch the variation of V out with T between T is equal to 0 and T is equal to 2.0 capital T. Capital T is representing the time period. We have already discussed, in this case we are using bridge rectifier. So the V out is full wave rectification. So we can write down here. So V out is full wave rectification. So this is full wave rectification because we are using in this case bridge rectifier. Full wave rectification simply means that current flow only in one direction. So when this is negative, due to full wave rectification, mean due to bridge rectifier, this one will be positive. So we can draw this one here. So simply if I look at this one, I can draw this one, then I can simply copy. So I can draw this positive part first of all. Now we can simply copy this one. So here I can copy this part here. And now we can move, so it means negative in this case become positive. We can again move this one, so this become also positive. Means the negative part in this case become positive. If we wanna move further, we can again move this one. We can also move this one to here. We can just place this one here first of all, and we can move this one here as well. And we can also move to this point here. So this is how we need to draw the full wave rectified signal. So let me clean little bit so you can get the better idea about this. We don't need this part, so we can clear this part. We don't need this part. We can also clear this one. So we can little bit make it better so it looks a bit better. So this part is not here. So this one here, and this also simply we need to draw like this. So this is full wave rectified, means the negative, just the reflection. So this is how you need to draw. Let me show you the proper one. So this is how you need to draw full wave rectified signal. So this is how we need to draw. Means simply the negative part is become positive, because in bridge rectifier full wave rectification simply means that current flows in one direction. Means the negative input becomes positive output. Second part says the power dissipated in the resistor is capital P. On figure 7.4, sketch the variation of P with T between T is equal to 0 and T is equal to 2.0 capital T. So first of all, we need to understand power, how this is linked with voltage. Power is equal to V square, V as a function of time divided by capital R. But we understand V as a function of time. This is equal to V naught, means the maximum value of voltage, time sine of omega t, sine of omega t. So the v square here we can write down, this will be v naught square sine square omega t divided by capital R. In this case, v naught is constant and R is constant, so the shape of the graph has to follow sine square omega t. And also we need to understand when v is maximum, for example v is maximum here, so it means power has to be maximum here. So v is maximum here, power has to be maximum. V is maximum at 1, so power has to be maximum here. V is maximum at 1.5, so you can see at 1.5, and V is maximum at 2.0, so power has to be maximum at this point as well. Now we need to sketch sine square graph, sine square. So halfway it has to be minimum. So here it is minimum, so power has to be minimum. So here it has to be minimum, here it has to be minimum, here it has to be minimum. Because V is minimum, so power has to be minimum. So we can see 1, 2, 3, 4, 5. So here it has to be minimum. So here it has to be minimum. In this case, it has to be minimum here, and it has to be minimum here. Now simply we need to sketch, so its shape has to be a little bit different. So it will go less steep at the bottom, then go somewhat like this. So this has to be the shape. But we can copy this one now, so we don't need to sketch again. So let me copy this part here. So we can copy because this will be the same pattern repeated. So we can take this one, we can place here. So at this point we can again place this one here, so it will be here. We can repeat this pattern because this shape will be repeated again and again. So this one will be the shape of the graph. So we can clear these points, so these points we can clear. So this is how this graph will look like. So what is the difference between these two? So you can see this is very steep here, so it has to be less steep at the bottom. You can see this trough, that less steep. So this trough. So that's the difference between these two. This is sine omega t graph, and this one is sine square. So this is the main difference between these two. Third part says, suggest with a reason how the root mean square value of V out compares with RMS value of V in. So first of all, we need to understand the difference between these two signals. We have rectified signal here. V out is rectified. So this one is rectified and this one is unrectified. So this is over V in. Now let's try to understand what is meaning of root mean square. Root mean square simply means that, imagine that we have a power supply, alternating power supply, and we connect this one across a resistor. And the resistance of this resistor, let's say, is capital R, and the peak value of this one is V naught. Now we have DC power supply, but we have the same resistor. So here we have DC power supply and we have the same resistor capital R. Let's say in this case power dissipated is equal to P naught. Average power dissipated is P naught. Now in this case we also need the same average power dissipated in this resistor. So we need P naught. So what value of V we have to use here? That value of V is the RMS value of AC. So let's say I have to use V here, and this V has to be equal to the RMS value here. So let's say this is V1. So for the same power dissipation in this resistor, V1 has to be equal to VRMS of alternating power supply. So this is meaning of RMS value. As RMS value is linked with power dissipation and average power dissipated, so it does not depend on negative value of V, or it does not depend on positive value. So it does not care about sign. So it simply means that VRMS for rectified signal and VRMS for unrectified signal. So we can say VRMS in has to be equal to VRMS out. So let me use small letters here. So we are using VRMS. So small letters VRMS out. So they are the same. We can also understand power average power dissipated, so we can write on here average mean power dissipated, or you can say average power dissipated. This is equal to Vrms squared by R. You can also understand, as we have the square here, so power does not depend on negative, or it does not depend on positive. So the shape of the power against time graph will be the same. It doesn't matter signal has negative value or positive value, as long as power will be the same, they have the same maximum value of the V. If maximum value of V change, then power dissipated will change, because RMS will change. But RMS does not depend on sign, positive or negative. So if this point is clear to you, I hope this is clear to you. So now let me show you the answer. In your answer, you can write down these points. In your answer, you can mention same power time graph with or without rectification. So same Vrms. You can say power does not depend on sign of V. So same Vrms. So that's all for this video, and these two questions we have discussed in detail. I hope these two questions are clear to you.